In accordance with the National Electrical Code, specifically the 2014 and 2017 editions, the practice of utilizing a conduit system as the sole means for equipment grounding is not considered permissible. The code mandates the installation of a separate equipment grounding conductor, often referred to as an EGC. Therefore, in the scenario described, it becomes necessary to rewire each receptacle circuit to facilitate the incorporation of these dedicated equipment grounding conductors. There are several reasons for this requirement. Firstly, a conduit system, over time, might not provide a reliable and continuous grounding path. This can be attributed to factors such as corrosion, the accumulation of rust, or the presence of loose connections within the conduit system. Secondly, the grounding connection established between the receptacle and the conduit itself might prove insufficient in ensuring proper and effective grounding. Thirdly, modern electrical codes have evolved to explicitly require a dedicated equipment grounding conductor for ensuring the safety and proper functioning of electrical equipment. To implement this, several steps must be taken. Firstly, new equipment grounding conductors, which are typically green or bare copper wires, should be run alongside the existing circuit conductors. Secondly, these equipment grounding conductors should be securely connected to the grounding terminal of each receptacle. Thirdly, the opposite end of the equipment grounding conductors should be connected to the grounding busbar within the newly installed distribution panels. It is important to note that, in situations where the conduit system is intended to be used as a supplemental grounding path, it becomes imperative to bond it to the equipment grounding conductor at multiple points to ensure effective grounding. Furthermore, the installation of ground fault circuit interrupters, commonly known as GFCIs, can provide an additional layer of protection against ground faults, further enhancing the safety of the electrical system. The NEC section 250.118 outlines the permissible types of equipment grounding conductors. These include copper, aluminum, or copper-clad aluminum conductors. The size of the equipment grounding conductor is determined by NEC table 250.122, which correlates the size of the overcurrent protective device with the minimum size of the EGC. For instance, if the overcurrent device is rated at 20 amps, the minimum size of the copper EGC is 12 American wire gauge. If the overcurrent device is rated at 30 amps, the minimum size of the copper EGC is 10 American wire gauge. And if the overcurrent device is rated at 60 amps, the minimum size of the copper EGC is 10 American wire gauge as well. When installing the equipment grounding conductor, it is crucial to ensure that all connections are made securely and are properly tightened. This is typically achieved using appropriate connectors and tools. The grounding busbar in the distribution panel serves as a central point for connecting all equipment grounding conductors. It must be securely bonded to the metal enclosure of the panel and to the building's grounding electrode system. The grounding electrode system typically consists of one or more grounding electrodes, such as ground rods, metal water pipes, or concrete encased electrodes that are connected to the earth. This connection ensures that the entire electrical system is at the same potential as the earth, providing a low impedance path for fault currents to flow back to the source. In older buildings, the grounding electrode system may not be adequate or may be missing altogether. In such cases, it may be necessary to install a new grounding electrode system to meet current code requirements. The NEC section 250.50 provides detailed requirements for grounding electrode systems. When retrofitting an older building with equipment grounding conductors, it is important to carefully inspect the existing electrical system to identify any potential hazards or deficiencies. This includes checking for damaged or corroded wiring, loose connections, and improper installations. Any such issues should be addressed before proceeding with the installation of the equipment grounding conductors. Furthermore, it is essential to ensure that the new equipment grounding conductors are properly supported and protected from physical damage. This may involve using cable ties, conduit, or other appropriate methods to secure the conductors in place. The NEC provides specific requirements for the installation of equipment grounding conductors in various types of wiring systems such as rigid metal conduit, electrical metallic tubing, and flexible metal conduit. In addition to the equipment grounding conductor, It is also important to ensure that all metal enclosures and equipment are properly bonded together. This includes metal junction boxes, metal light fixtures, and metal appliance housings. Bonding helps to create a low impedance path for fault currents and reduces the risk of electrical shock. The NEC section 250.92 provides requirements for bonding metal enclosures and equipment. Ground fault circuit interrupters, or GFCIs, are devices that are designed to protect against electrical shock by detecting ground faults and interrupting the circuit. A ground fault occurs when current leaks from a hot conductor to ground, such as when someone touches a live wire and gets an electrical shock. GFCIs are required in many locations, such as bathrooms, kitchens, and outdoor areas, where there is a high risk of exposure to moisture. When retrofitting an older building with equipment grounding conductors, it is a good practice to install GFCIs in these locations to provide additional protection against electrical shock. The NEC section 210.8 provides requirements for GFCI protection. Another important consideration when retrofitting an older building is the capacity of the existing electrical system. Older buildings may have electrical systems that are not adequate to handle the increased electrical loads of modern appliances and equipment. In such cases, it may be necessary to upgrade the service entrance, panel boards, and wiring to increase the capacity of the electrical system. A licensed electrical contractor can assess the existing electrical system and determine the appropriate upgrades that are needed. The NEC provides guidelines for determining the load calculations for electrical systems. When working with electrical systems, it is essential to follow all safety precautions to prevent electrical shock and other hazards. This includes wearing appropriate personal protective equipment, such as rubber gloves and safety glasses, and energizing circuits before working on them. It is also important to use properly insulated tools and equipment. Only qualified and licensed electricians should perform electrical work. In summary, when retrofitting an older building with equipment grounding conductors, it is important to understand the NEC requirements, carefully inspect the existing electrical system, install the equipment grounding conductors properly, bond all metal enclosures and equipment together, install GFCIs in appropriate locations, and ensure that the electrical system has adequate capacity. By following these guidelines, it is possible to improve the safety and reliability of the electrical system in an older building. Remember to always consult with a licensed electrical contractor for specific guidance on your project. The information provided here is for general educational purposes only and should not be considered a substitute for professional advice. Now let's delve deeper into specific aspects of equipment grounding conductors and their implementation. The material of the equipment grounding conductor is crucial for its effectiveness. Copper is the most commonly used material due to its excellent conductivity and resistance to corrosion. Aluminum can also be used, but it must be size larger than copper to provide equivalent conductivity. The size of the equipment grounding conductor is determined by the size of the overcurrent protective device protecting the circuit. As mentioned earlier, NEC Table 250.122 provides the minimum size requirements. It is important to note that the equipment grounding conductor must be installed in the same raceway or cable as the circuit conductors. This ensures that the impedance of the grounding path is minimized. The impedance of the grounding path is the total opposition to the flow of fault current. A low impedance grounding path is essential for quickly clearing ground faults and preventing electrical shock. When installing equipment grounding conductors in metal raceways, such as rigid metal conduit or electrical metallic tubing, the raceway itself can serve as the equipment grounding conductor if it is properly installed and maintained. However, it is still a good practice to install a separate equipment grounding conductor inside the raceway for added redundancy and reliability. When installing equipment grounding conductors in non-metallic raceways, such as PVC conduit, a separate equipment grounding conductor must always be installed. Non-metallic raceways do not provide a conductive path for fault current. The connection of the equipment grounding conductor to the grounding terminal of the receptacle is a critical step. The connection must be made using a listed connector or terminal that is specifically designed for grounding purposes. The connector or terminal must be properly tightened to ensure a secure and reliable connection. The connection of the equipment grounding conductor to the grounding busbar in the distribution panel is also a critical step. The grounding busbar must be securely bonded to the metal enclosure of the panel and to the building's grounding electrode system. The connection of the equipment grounding conductor to the grounding busbar must be made using a listed connector or terminal that is specifically designed for grounding purposes. The connector or terminal must be properly tightened to ensure a secure and reliable connection. The building's grounding electrode system is the connection to the earth. The grounding electrode system typically consists of one or more grounding electrodes, such as ground rods, metal water pipes, or concrete encased electrodes. The grounding electrode system must be installed in accordance with NEC section 250.50. The grounding electrode system must have a resistance to ground of 25 ohms or less. If the resistance to ground is greater than 25 ohms, an additional grounding electrode must be installed. The purpose of the grounding electrode system is to provide a low impedance path for fault current to flow back to the source. This helps to quickly clear ground faults and prevent electrical shock. In addition to the equipment grounding conductor and the grounding electrode system, it is also important to ensure that all metal enclosures and equipment are properly bonded together. Bonding is the process of connecting metal enclosures and equipment together to create a continuous electrical path. Bonding helps to reduce the risk of electrical shock by ensuring that all metal surfaces are at the same potential. Bonding is required for all metal enclosures and equipment that are likely to become energized. This includes metal junction boxes, metal light fixtures, and metal appliance housings. Bonding is typically achieved using bonding jumpers, which are short lengths of wire that are used to connect the metal enclosures and equipment together. The bonding jumpers must be sized according to NEC Table 250.102. The bonding jumpers must be installed in a manner that provides a lower impedance path for fault current. This may involve using bonding bushings or other special fittings. In some cases, it may be necessary to use exothermic welding to create a permanent bond between metal enclosures and equipment. Exothermic welding is a process that uses a chemical reaction to create a molten metal bond. Exothermic welding is often used to bond grounding electrodes to metal water pipes or other metal structures. Ground fault circuit interrupters, or GFCIs, are devices that are designed to protect against electrical shock by detecting ground faults and interrupting the circuit. GFCIs are required in many locations, such as bathrooms, kitchens, and outdoor areas, where there is a high risk of exposure to moisture. GFCIs work by monitoring the current flowing in the hot and neutral conductors of a circuit. If there is a difference of more than 5 mA between the current flowing in the hot and neutral conductors, the GFCI will trip and interrupt the circuit. This indicates that some of the current is leaking to ground, which could pose a shock hazard. GFCIs are available in several different types, including receptacle type GFCIs, circuit breaker type GFCIs, and portable GFCIs. Receptacle type GFCIs are installed in place of standard electrical receptacles. Circuit breaker type GFCIs are installed in the circuit breaker panel. Portable GFCIs are plugged into standard electrical receptacles. When retrofitting an older building with equipment grounding conductors, it is a good practice to install GFCIs in all locations where they are required by the NEC. This will provide additional protection against electrical shock and help to ensure the safety of the occupants of the building. In addition to GFCIs, arc fault circuit interrupters, or SIs, are also designed to protect against electrical fires. SIs work by detecting arc faults, which are dangerous electrical conditions that can cause fires. Arc faults can occur when there is a break or short in a wire, or when there is loose connection. SIs are required in many locations, such as bedrooms, living rooms, and dining rooms. SIs are available in several different types, including circuit breaker type of SIs and outlet branch circuit of SIs. Circuit breaker type of SIs are installed in the circuit breaker panel. Outlet branch circuit of SIs are installed in the first outlet in the branch circuit. When retrofitting an older building with equipment grounding conductors, It is also good practice to install a size in all locations where they are required by the NEC. This will provide additional protection against electrical fires and help to ensure the safety of the occupants of the building. The NEC is a comprehensive set of standards for electrical safety. It is important to be familiar with the NEC requirements when working with electrical systems. The NEC is updated every 3 years. It is important to use the latest edition of the NEC. The NEC is available from the National Fire Protection Association. In addition to the NEC, there are also local electrical codes that may apply. It is important to check with the local authorities to determine which electrical codes are in effect in your area. When working with electrical systems, it is important to follow all safety precautions. This includes wearing appropriate personal protective equipment, such as rubber gloves and safety glasses, and energizing circuits before working on them. It is also important to use properly insulated tools and equipment. Only qualified and licensed electricians should perform electrical work. By following these guidelines, it is possible to improve the safety and reliability of the electrical system in an older building. Remember to always consult with a licensed electrical contractor for specific guidance on your project.